And we are on Tuesday, the 27th. It's class number 10, packet 6. Let's see what's happening today. Now I have I put all the help videos I will up on. They're either two places. One is in the YouTube channel under the test 6A practice problems, and that's going to hodgepodge in there. But if you go in there, you can figure out which one it is. Sometimes it has a title on it, sometimes it doesn't. Like let's say practice problem number 15 or something. But the other place it's more obvious, is the guide number 3 in the Facebook, where underneath the problem, it is in the comments. It goes right to them, the one that goes with that. Here's an example of the little boat being towed by the big boat, and this is just showing you the final scene of that 2-minute or so video, or 2 or 3 minute video, where I go through all of these things one at a time. So it does help to watch those. You're silent, so you don't need to worry about your volume or somebody. You can watch it while you're watching TV, or pause it or watch sitting in class. Not that you should do that, but. And then here's one where the helium balloon, where we start off with a head to tail and we work our way to free body diagram, and then we have the equations. But that's in there as well. That shows how to do it. I ran across this picture, and this is, we do talk about force of thrust. And in force of thrust, you have m dot VE, right? M dot is how much mass is coming out the back per second. So kilograms per second. I don't know what this is. This is in the Falcon Heavy. This is not last summer, but the summer before last, when it lifted off. And then the VE is how fast that's coming out. So if you're putting out 100 kilograms per second, and these kind of rockets do this, and you're putting them out at, say, Mach 1.5, that multiplies together to make quite a bit of thrust. You need that because this thing weighs tons. I don't know how much the Falcon Heavy weighs, and it's got a payload on it, so it's really heavy. You got to get off the launch pad. I got this from a student a couple days ago, and he's in Germany, Tim Yallis, and he said, I just passed my final teaching exam last Wednesday, so from now on, I'll be stepping in yours and others' footsteps. And I said, that's fantastic. What are you teaching, Tim? He said, I'm currently teaching science and physics and math. So that's kind of cool. I think of the 5,000 students I've had, probably only 5 or 6 have taught physics, have gone on to teach physics. So that's a pretty rare community there. And a lot of them are still physics teachers now. So I'll be teaching physics in Germany. In Germany, by many accounts, we consider the kind of the heartthrob of the heartbeat of physics, historically and currently, even pretty strong still. All right. I did a little stargazing today. We finished up 6.2 and 6.1 today. So I'll post those keys. Now, hold it though. I just realized this. I'm not going to post the key to 6.1 until you guys have turned it in. So for you all, your 6.1, not 6.2, but 6.1 is due. And let's make this due tomorrow night. So due Wednesday at the usual 11:59. Okay. So we've gone through all of them. We'll finish the last 2 today. So they're all, in previous, but I hate to post the key, just copy off the key, but anyway, so tomorrow at midnight, that's due for you. And I haven't posted yet because I don't know how many points to make it worth. but I'll add up the stamps we've had on so far and I'll make it worth those points. Well, 14 stamps so far. So 14 stamps, and some of that includes 6-2, but we're kind of, as far as points go, so we're looking at 42 points. So I'm going to make it 40 points. That's a lot. So 40 points for you to turn in, you virtual students, to turn in, to submit it. Don't submit it yet because I got to put this, I got to add, I'll add this to your assignments, to virtual assignments. Okay. Meet table 4. I met my table 4 today. Anybody here? I'll turn the, I'm going to turn this off, recording. And anybody wants to be met, I'm going to pause recording. Oh, turn off your, if you don't mind, turn off your. All right. Very good. So we got to meet IO and found out about what he's thinking about doing. All right, so today's physics. We're going to look at the homework a little bit. I'm just trying to follow what we did in class. Let's look at 11 real quick. And 11, the reason I want to bring up 11, it's a pretty easy problem, but the reason I bring it up is the wording. And I underlined it here, but see where it says total force, that if you see it that way, or you see it say net force, either one, in the equation, or total, in the equation, that means summation of forces. So this is telling you that so we have a free body diagram, but I kind of gave away the ship when I say total force. So we have summation, we have the force of thrust up, we have mg down, maybe we have a little air drag, it doesn't matter. We have mg down, we have ra down, because they got that. I have summation of forces. So summation of forces is mass times acceleration. So I already know that's 10.2 newtons. So 10.2 newtons equals, now the mass, I've got to pull the g out of the weight, equals 14.7 newtons divided by 9.81 meters per second squared, times ay. Okay. And then you solve for ay equals whatever. I have the answer down there at the bottom. So looks like it's 6.81. All right, fair enough. But the point there was, when it says total or net, that means they're giving you the summation of forces. Hopefully you tried the homework. This going over homework always makes a lot more sense if you've tried it, even if you got it wrong. That's the whole point behind stamps. Now, the one like 12, I want to work, and I want you to quote, go to the board. So I'm going to turn off the camera here in a minute, or not the camera, but the recording in a minute, and let you try this one, because this is more like the one that's on the practice problems, which means that there's a possibility to be on the test on Friday for you guys. Okay, Thursday for in-class kids, Friday for you. All right, so I'm going to hit pause again and let you work on this one on your own. If you haven't, if you have, just chill for a minute. All right, so I don't know what you did, but here we go. Let's see what you're supposed to do. So we do a free body diagram. Now, you go, well, I need to include air drag, but it didn't list air drag. So it doesn't list it, you don't include it, only because there's nothing you can do with it. You're going to assume it's negligible, and it could be on a rocket. Rockets don't have a whole lot of air drag. I mean, they do because they go so fast, but they're pretty aerodynamic. I mean, as far as not putting a big profile area towards the direction of motion. So we're going to have to assume that it's negligible. So force of thrust is 7840. No, I got it wrong. Force of thrust is 10,440. And the weight is, that's 800 kilograms. That's a huge, like a car, like a small car being lifted off the ground. Okay, so you have there's our check. We did our FBD. Now we do summation of force equals mass times acceleration. And so we say, okay, that is force of thrust is positive remember in a free body diagram, the direction motion is positive. Minus mg opposes motion equals ma(y). I'm trying to solve for ay, so I can plug in my kinematics. So ay, I'll just go ahead and plug in the numbers here, is 10,440 minus 7,840 divided by m, which is 7,840 divided by 9.81. I got to pull the g out. Newtons. I'll tell you. Hold. I'm gonna do this. I'll be lazy. Put brackets around the whole thing. Just put kilograms, because they'll end up being kilograms, right? You end up with ay, if I remember this morning, 3.25 meters per second squared. Not a huge, you go, man, that's a lot of thrust and not much acceleration. That's because I'm trying to get this car to lift off the ground. And it just takes a lot of, like when you watch these launches of these Saturn V's and these Falcon Heavies, and it's just lifting slowly, but yes, it's got to build up acceleration. It takes time. So the last thing is to then use your orange kinematics, and your first orange will do. So we have V final equals V naught plus AT. Well, V naught is 0, we have to assume on the launch pad. So V final then equals 3.25 meters per second squared times 10 seconds. And so final velocity is 32.5, which is not that fast, but that's up to 10 seconds. Meters per second. Okay, any questions on that? That officially finishes 6.2. 6.3 would be pretty quick. So I think we'll move in. 6.4 is gold standard. I hate to tell you that. It's our last gold standard of the year. And then 6.5 is angle. So we'll get through boom, 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 boom. Next thing you know, we're through 6.7. That'll go real fast in the next couple of weeks. We'll probably get to about 610, and then we'll see. We may have to wrap it up in June, but okay. So yesterday we talked about fluids. About fluids and about buoyancy, air being a fluid as well. 3 things involved for buoyancy. If you know the density of your fluid, where it's at, and that changes, as we saw yesterday in that table, where you're at above the head, that density goes way down. So buoyancy, so the air loses its ability to lift. Take a look here. Let's go back and look at that for a second. Hold on, right here. Oh, and I added this to the screenshots. So look, above us we have the troposphere. That's where pretty much all of weather is. And then above that is the stratosphere. In the stratosphere is the ozone layer. And then above the stratosphere is the mesosphere. And then above that's the thermosphere. So they're like 90 kilometers, 80 kilometers. Well, if we take that altitude up, this is showing what it is, what density, what pressure is. Pressure and density are very closely related. So, but look at this. On Earth, that's actually, this is in the ocean, but on the surface, 1.2 kilograms per. Oh, no. That's not in the ocean. This is not in the ocean. It's in like Death Valley. It's like in a low point on the Earth. So that's not in water, because it's a whole different density. But anyway, so 1.2 is about what it is here on land. But if you notice, as you go up, you get up to, as we showed yesterday, you get up to, look how small it gets up at, even at 25 kilometers, just 25 kilometers, you're up here at 0.04. Planes fly at, what, 5 miles, somewhere in there, so maybe 7 or so. Say planes fly up in here, so like jets. So remember that air drag RA. Yeah, so you have planes here sitting at about 20 kilometers, about 22, 23 kilometers, and anywhere between 10 and 22 kilometers. Probably looks like jets, they're showing more like 12 or so. So they're more like in here. They're more like in, let's say right here. So this will be jet in this range, not that. So the air drag up there, RA, remember, is 1/2 d rho a v squared. Well, that rho is this rho. So if I can drop that rho from 1.225 to 0.46, that's about 3 times less. So it's 3 times less air drag. It's a direct relationship. So 3 times less air drag where these 747s fly, or 737s or whatever. Okay. Sorry, where am I? Okay, so that's the rho part of buoyancy. And yes, there's buoyancy in a 747 as well, but its MG is so big, it doesn't have a chance. So when you get to a certain height, like a balloon goes up, a helium balloon takes off, it needs that buoyancy. It leaves your hand, it's gone. But then it's going to eventually reach a point where the buoyancy, the rho, is low enough, the volume's going to actually get bigger. You let these twice a day, they let these weather balloons go in Norman, South and North Norman, about 6 o'clock in the evening. If you go out there, you can watch them. They're hydrogen filled, and they're about, if you can see me, they're about as tall as me, the balloon is, and then it's about, as wide as me. So it's kind of fairly roundish. But then they let it go, and then this thing, as it goes up in the air, the buoyancy just takes off, man, it's gone. But it starts to get bigger, it's elastic, so it gets as big as a house. And finally it pops. And then it comes back down, a little parachute comes out, a little radio sonde that it's attached to, it's measuring all this information, dew points and all this stuff. And then it falls back down to the earth with a parachute. And then you pick it up and you put it in a mailbox and send it back to the National Weather Service. They do it again. Anyway, I don't know if you've ever seen one of those in your backyard, but you do see them lying around. But the point is that as that thing rises, this is going down, 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 down. And eventually the air loses its ability to lift that balloon up because rho gets so small. G is not going to change much, as we saw yesterday. And the V will go up, but not at the rate that the rho is going down. Okay. Yesterday we talked about the submarine. We talked about Indonesia, what's going on. It lost, the submarine went at the bottom of the ocean, at the bottom of the ocean there at 3,000 feet, which is pretty bad. 5 miles down there. The water pressure there is unbelievable. Even most submarines really can't even go down there. They're gonna, and it probably collapsed. It's sort of like a Coke can. It just collapsed in that water pressure. So yeah, hope they had a fast death, not just drowned. But the problem is, one of the things that might have happened, they're going to do a CSI on it, but I'm guessing that one possibility is that these compressed air tanks that push out the air, like if you watch a submarine, you'll see these bubbles coming up, that they're trying to rise. They're pushing the air, they're pushing the water out. And so that gets all the water out of the ballast tanks. And it's really hard to do because remember, the surrounding pressure is huge of this. So it's hard to push water out when you're pushing into so much PSI, pounds per square inch, outside the hole. So you have to outdo it. And these tanks, these motors go out on you. So it could be that there's backup systems, but it could be that they lost that power there. They might have been breached. There might have been an explosion on board and the hole got breached, and that was it. Anyway, we'll find out in the next month or so. It'll take them a while. So if I'm submerged and I want to go to rise, I push this. Blue represents the water in the hole. The yellow represents the air. It's a simplified view, of course. I then push all that water out, and that makes me rise. If I am already in port and I want to drop, I open up these valves down here, and then the water naturally comes pouring in, and then the air, it comes out this way. So it's probably when you see a submarine diving, the little bubbles are coming out because it's pushing out the air. Okay. All right. Stop me anytime. And then we talked about in port. My mentor teacher, Mr. Fix, in Vietnam War, was on a diesel sub, and in port they would, when they're in their bunks, him and his buddy, bunk to bunk, across the hull, would put this tight cable, and it was tight in port. But as they got to depth, a whole cable started bending in because all that just showed the whole of the ship was being crushed like a Coke can. And they could tell how deep they were by how far by this. They had a little system developed where, you don't always, this is an old diesel sub. So it was mostly manual and, click buttons and stuff. So they didn't have a lot of information they could just refer to. So they could tell their depth by how far that cable was bowing. Okay. And then the last thing let's talk about is fish. How do fish rise? I could see a submarine has ballast tanks, but how does a fish, like a goldfish, how does it go up and down in your aquarium? Any fishermen out there? No? Okay, well, the answer is when a fish has what's called a swim bladder. And so inside a fish, these fish rise and sink in water by controlling how much air is in the swim bladder with they constrict their muscles. This is an actual picture of a swim bladder. You don't eat that. So when you first skin a fish, and I'm no fisherman, when you first skin a fish, though, you pull out that swim bladder. Somebody in my last hour said, "Oh yeah, you toss that." Here's a more of a dissected fish where it shows the swim bladder up there, right above the ovaries. Here's a cartoon of it. Swim bladder muscles relax. It gets bigger, then the fish is lighter. Because more of the fish is air, so the density of the fish becomes less than 1 gram per mil. The fish then floats up, and then the bladder muscles tighten up, get smaller. That means the fish becomes more dense than 1 and then can sink in water. So man, it's that's pretty crazy. You ever thought of that one? So it makes you think, it must be in some kind of intelligent design or something that caused this, and that's the way some people think. Makes sense. I can get it. It's called intelligent design, and a lot of physicists believe that there's so much complexity to the world. The blind watchmaker kind of thing. My thought is that say what you want about religion and all, but my thought is that we started evolving, in water. So we've had a lot more time. Fish are more evolved, I suppose, than humans in the ways that you would think. Well, I take it back, because we started as fish, if you believe evolution and all. Okay, I'm going to assume we do, but you start as fish, and then you worked your way up to land, and then you started walking. So I guess we still came from fish, still have the gills and all that. Anywho, so it's kind of cool so I wonder if humans used to have a swim bladder and that became our lungs. I guess my biology is really lacking. So I probably ask stupid questions in biology. That's probably an obvious thing. Yes, of course, Asky, that became your lungs, dummy. Maybe not. I don't know. Anybody that's really good at biology, let me know. Here's another mock-up of that showing that, where that swim bladder is in fish. So here's the next question is, sharks who go really deep, how do they do it? Sharks don't have swim bladders. How do they rise and fall in the water? This is one I did not know. I knew about the swim bladder, but I did not know about sharks until a few years ago. I looked it up. Sharks use oil in their liver. So they get their buoyancy from an oil-filled liver. And the same idea, though, they can constrict or contract their muscles and make that smaller, or they can expand it and make it bigger. So, you know, density is mass per unit volume. So if you make more of your volume a lower density thing, anyway, that's what sharks do. So they can rise and fall. And buoyancy is still the same. Buoyancy is going to go up the further down you go because density of water goes up so high. All right, so that should wrap up density. Now let's look at.
Mr. Ashley.
Yeah.
So back to the sharks thing. Wouldn't they also like use their tails to?
Yeah. Oh,
like,
that's for you know, moving along. And someone said that too another hour. So well, they just kind of float, and just with that case, why don't fish just do that? Because you need something else beyond just flapping your, you know, your fins. You've got to because you have this buoyancy and you have pressure all around you, but your weight's holding you down. So you have to have something else to kind of help get you lifted up. So yeah, but that does, of course, get them going. It's kind of getting up a hill. You know, you got a little oomph. You get a little more oomph. Yeah. All right. So let's look at number 11. This is on 6.1 again. We're going to wrap up 6.1 today. So I got to hurry here. Number 11. I've been sitting here yapping too much. Number 11, we have a tennis ball. And this tennis ball, we're throwing it on the court, and it's smashing down, and it's ready to rebound. Okay, something weird, really weird happens here. So here's the tennis ball, and it's got a little mg. Not much, just a little mg. It doesn't weigh much. And then you'd think, well, the normal force looks like this, right? Because it counteracts mg. But no, in this case, the normal force is much bigger than mg. We actually did the math one year. It's like way up here, the normal force. To get it to go to its height, the normal force is way up here. And this is a weird normal force. Normal forces are weird, but this normal force, it's a suitcase. So it's a normal force suitcase. And this suitcase contains, the contact, the normal contact you would have, which is the weight, counters weight, mg. I'll just say weight. Weight and mg is the same thing. Okay. And it contains the spring force. And I should have put spring forces on the front. Go back to the front where it has your table of forces. Add capital T for tensile force, and add F sub S for spring force. Spring force. And so it's like the tennis ball is a compressed spring, and it's ready to fire back up. Okay. So, and that reminds me, we'll do the spring dance probably Friday, because we have to have it done by the prom. The prom is Saturday. So we're going to have to go outside unless it's raining and do the spring dance so they can do it at the prom. But the spring dance involves kind of how the spring's force changes. It's Hooke's law, basically. How the force changes, the spring force changes with compression or stretch. So I'll take some video of it. But now we come down here, we say, okay, so normal force minus mg. Now the ball's sitting still. It's not moving. So it's got to equal 0, right? But there's no way that force minus this force, that ain't 0. So it's equal to MAY. But now you go, wait a minute. It's not moving, but it has acceleration. It doesn't have velocity, but it has acceleration. The answer is yes. It's like something at its apex. It still has an acceleration of negative 9.81. I mean, G is down, if we assume G is down, but it doesn't have any velocity at that particular instant. So this ball was going down. The velocity is in the process of changing directions and going up, and that's where acceleration is the greatest. To get that velocity to turn around, to get that vector to go from down to up, that takes the most acceleration of anything. So acceleration is actually maximized. Not only is there acceleration, it's the most acceleration that tennis ball is going to get, even though it's not moving. Physics is weird sometimes. Okay, last thing for today, in the time we have left, about 10 minutes, we did 12A, 12B because there's a good shot. This is like the practice problems, PP 20 and 21. Okay, so we're going to kill two birds with one stone. So I had them go to the board, and I don't have time to let you just kind of wander up at the board on your paper. We're going to have to kind of go over it because I got to get this thing done by 2. All right, so here we go. So I apologize for pushing this thing through, but let's say a bowling ball is sinking in water at terminal speed, at VT, with terminal velocities, same thing. Okay, so it's at terminal speed, meaning we drop the bowling ball in water and it will sink real quick, but eventually the water buoyancy starts to catch up with the weight, and it eventually makes it so let's say it's at the point now where it's still sinking, but it's not everything's sinking at a constant rate, or pretty much a constant rate. All right, that has problems with it as well, that concept, but let's take a look. So bowling ball sinking in water. Oh, this is a 16-pound ball, let's say. So that's really heavy. And we'll make a big mg down. There's 2 forces up, right? There's buoyancy, which is always up, and we're saying at VT. So buoyancy's up of water. Don't put B sub A, puts B sub W. And then drag. There's water drag. There's a lot of water drag on a bowling ball. I don't know which one's bigger. I do know this. So this is RW up. Now, on these, you've got to show direction of motion. The old yellow, I make mine yellow. The old arrow. Okay, so I'll put a little plus in the end just to indicate down is positive here. So we have that situation. So in this case, the summation of forces is, and let's say it's at terminal speed. So we'll say at VT. So in this case, we have mg, direction of motion is positive. Mg is positive now, minus the buoyancy, minus the drag, and that's going to equal 0 because I'm at terminal velocity. I'm not speeding up, slowing down. Okay. So far, so good. Still got 9 minutes. Okay. Now, since we have a little bit of time, now you do B. And let's say bowling ball is rising in water, not at terminal velocity. It's a weird concept to think terminal velocity going up, but it's rising in water. And let's say that you just let it go. You push it down, and you go, wait, bowling balls don't rise in water. Yeah, they do. If they're 8-pounders or less, bowling balls will rise in water because their density is less than 1. And so anything with density less than 1 will rise in water. You rise to kind of your level of density. You've seen those columns in chemistry. I used to, first day of class, I would take a big column of different fluids and I'd drop things in them, and some would stop here, some would stop here. We talk about miscibility and all that. Density. Anyway, so that's sort of the same idea. The ball is rising and buoyancy is changing as we go. Because remember buoyancy of water or of air is the rho, the submerged volume, which in this case, the whole thing is submerged, and G. Those 3 things. G is not really changing much. The volume of the bowling ball is not going to change. It's already submerged. So the only thing that's changing is this is by the way, the density of water. It's not the density of the ball. It's the density of water, the displaced water. So it's hard to say it's constant, even back in A, it's hard to say it's constant velocity because buoyancy is always going up, but then RW goes down. So, all right. So here we go. I stalled long enough. Here we go. So now the direction of motion's up. It's rising. That flips everything. So I'll make that my big fat yellow arrow. Put the little plus sign in the tip. And here we go. Buoyancy, guaranteed, always up. It's rising, so I'll make that like that. And then the MG, this is a lesser MG. It's like an 8-pound ball versus 16. MG is still down always. And this time the RW is down, it flips. So RW is down. And these have to, now the buoyancy up has to beat the MG and the RW down. So in the summation of forces, we have buoyancy of water is positive, minus RW, minus MG equals MAY, because we said it's not reached terminal velocity yet.
So why would the water drag be less?
Well, I'm saying that, and I think let's show you this. Okay, last year when I did this, we actually did put numbers to it. So when I throw, we talked about a 12-pound ball. I guess I was wrong. I thought 8 pounds was the cutoff. It's 12 pounds. So a 12-pound ball will rise like a kiddie ball at Sooner Bowling. So I actually put numbers to this. So here I made both of them, I think, terminal speeds. But here I said, okay, the bowling ball is 16 pounds. The RW is 4 pounds. And so I did compare the two. The buoyancy is 12 pounds. So at the same level, the buoyancy is still going to be the same, right? Because its density is the same. That stays 12 pounds. The ball switched to 8 pounds. Therefore, our drag is still 4 pounds, depending if it's going the same speed. So that's putting numbers to it. But back here, these two, I didn't say it's the same. It's not the same ball. It's not the same height. It's not the same column depth in the column. So all I got to do is make sure that when I add up these two, this one and this one, I get something less than this buoyant force up. All right. I got to have more buoyant force up than I do force down if I'm going to get an acceleration up. I suppose if they were bigger, you could have a negative acceleration and it's just slowing down. But now that I think about it, why wouldn't it just slow down? I have to rethink this because I normally have these at terminal velocity. I don't usually have them accelerating. But now that I think about it, no. It's rising. Oh, it could be. Okay, so it could be rising, but slowing down to a point. My experience, you take a beach ball and you put it in a swimming pool, let it go. It goes, shoots out of the water. It seems to be gaining speed the whole way. Then it finally breaks the surface and goes up, So I'm going to stick with this, I guess. We'll consider it still a positive acceleration. I got to think about that a little bit, though. Bowling balls in water is kind of complicated, actually. Okay, so that does it. Hold on a minute. Did that. Oh, so tomorrow, what we're going to do is to get them to come. A lot of times they like to stay home like you do, right? On Wednesdays, they want to sleep in or just not. I mean, I know you guys don't sleep in every day, but they want to do their thing on Wednesdays. So hard to get them to come. So I have to offer incentives to get them in the classroom. But one of the things I'll do tomorrow, if you're here live, I will give you some Easter eggs for the test on Thursday. Now it's not like it's not like a test B where I can hold back 10%. I can't. Everything that is on that test has to come from the practice problems. It's like a lead pipe guarantee that's going to be there. But what you don't know is which of those 22, probably like 9 of them. I haven't written the thing yet. Probably about 9 of them will make it. if you see the same kind of problem repeated on the first set as the second set, like in both cases, there was a head to tail to free body diagram to F equals MA. So you know there's going to be one of those, guaranteed. And then you saw a gold standard on the both sets. So therefore, there's going to be a gold standard. So those are the two you can count on. But I'll try and give you a little more heads up tomorrow in the live session. I'm trying to give kids incentive to actually show up. So I can't, if I record it, then they're just going to wait for the recording. So be here early on tomorrow, and I will give you that. And then we're going to work on this, which is really 6.3. It's not new material. It's those wooden arrows, and we're going to work on those tomorrow. Okay. And then, like I say, some Easter eggs, and maybe I'll answer some questions, last minute questions for the test on Friday for you guys. We won't meet Thursday. There won't be one of these Thursday. Okay. Actually, won't be one of these Friday either. So tomorrow is our last day for this week. Okay. Friday, you'll just get the email. All right. So